So in this question, we're told the volume scale factor says it has a scale vector volume for volume of 64x cubed, and it throws people. There's no pictures of shapes, but you just have to think what you'd usually do. It seems to be algebraic, and you just think what you would usually do if you had a numerical volume scale factor. So again, when you've established a scale factor, you should always write it down. So let's write that down. So let's write the volume scale factor is 64x cubed. And it's asking for a scale factor of area. And remember, to get any scale factor, really you need to go back to the length scale factor. Now we know from our diagram, let's just quickly get it down. We have LSF, ASF, VSF. Okay, here you square, here you cube. But we need to go back from the volume scale factor back to the length scale factor. So we need to cube root. So how does that work? So if we have the length scale factor, we need to cube root this. Okay, we need to cube root the whole of 64x cubed. It's a bit like our work on powers, that when you're squaring something, the whole of something, you have to square both bits. We should recall that 2x all squared, the 2 has to get squared, and the x has to get squared. So it's the same here. If you want to cube root 64x cubed, you have to cube root the bits separately. The cube root of 64 is 4, and the cube root of x cubed, well, if you cube something and then cube root it, or cube root something and then cube it, they just cancel each other out. If you try it with a number, if you do 2 cubed is 8, and then you cube root it, you go back to 2. So basically, the cube root of the x cubed is just x, which means that the length scale factor is 4x. However, they're asking for the scale factor for area. So once we at the length scale factor, we then need to square it. So the area scale factor would be 4x all squared. You have to square the whole of 4x. Again, same principle. The 4 squared is 16, x squared, and the answer is 16x squared. The actual answer has to be in terms of x, because the volume scale factor is in terms of x. So you're not going to get a number answer. Okay, it's going to be in terms of x. So that's the answer to question 7, 16x squared. Okay, question 12. We're told that these two triangles are similar, and my recommendation is always to draw the two similar shapes side by side, both looking to have the same orientation. They both have a right angle. You can see they're both right angles, therefore they both have a hypotenuse. So let's draw them side by side, like for like. So the triangle at the bottom we can see is 3. Right angle there, hypotenuse there is 4. This one here, I'll draw next to it. What do we know in that one? Well, we don't know the base, we don't know that. The only thing we know is the hypotenuse, which is x, right angle. But we're told these are similar. Okay, not all right angle triangles are mathematically similar, but we're told in this question that they are. The issue is here, how do you get a length scale factor? Because I've got the 4 here, I don't have it there. If that was 8, I could say it's, the length scale factor is 2. The 3, I don't have either. So what you have to think is slightly outside the box. What do we have here? We have right angle triangles. What have we learnt about right angle triangles? Right, we have Pythagoras. Okay, Pythagoras is a theorem that applies to right angle triangles. That is, just the length. Okay, so we can say 3 squared plus 4 squared is this unknown here. I don't use x because there's x over there, so let's just create y. Okay, equals y squared. Now 3 squared is 9, 4 squared is 16. You add 16 and 9 together, you get 25. So y therefore is 5. Okay, using Pythagoras. And now comes the clever bit. You might say to yourself, well, how am I supposed to get the length scale factor? Fine, I know that's 5 and I know that's x, but I don't know x, I don't know the value of x. So, the question asks you to find the value of x. So we saw a similar idea when we did work on Pythagoras and trigonometry. We've now found that that length is 5. This length here is 5. But look at the diagram. That 5 there forms the base of that triangle there. So that 5 is not only that length there, this hypotenuse, but it's also the base of this one. So now this is 5. And now we have two corresponding lengths and we can get a length scale factor. That's 4 and that's 5. So therefore the length scale factor is 5 over 4, the ratio 5 over 4, which is 1.25. And then you just apply that length scale factor the same way. From 4 to 5 must be the same ratio increase from 5 to x. So if we multiply 5 by, you get 6.25. Okay, so don't rule out having to use other bits of maths in certain topics we do. Yes, we're dealing with similar shapes, but as soon as you see a right angle triangle, you have to entertain the idea, I might have to use Pythagoras if lengths are involved, and we've also learnt about angles. Maybe trigonometry, SOHCAHTOA might have to apply. Clearly it doesn't here because there's no angles involved apart from the right angle. Q13. So once again, you can see these arrows here, which tells us those lines are parallel, which usually opens up the door for some similar shapes. Once again, I recommend to draw the two similar shapes side by side, separate. So you can see this small triangle here is going to be similar to the big triangle. Why? Because they both share that angle there. Okay? And this angle and this angle are the same, since those are parallel. And corresponding angles, this angle here corresponds to this angle there. Again, that only works because they're parallel. So it means that the small triangle, which is nested inside the big triangle, will automatically be similar. That will always be the case, as long as you have those parallel lines in play. So anyway, the small triangle, let's draw it with the length just for the small triangle. So what do I know about the small triangle? The base is x, it tells me that. The height is 3. And what about the big triangle? Again, just look at the big triangle. The big triangle, you have 4. Now the base is the 3 and the x. You've got to join the 3 and the x together. So let's say that's x plus 3. So we've got a lot of algebraic lengths here. However, just think what you would normally do and just go with it. So I can see here that the 4 and the 3 correspond, so there's a length scale factor there, and then you've got the x and the x plus 3. So you could work out the length scale factors 4 over 3 and then multiply it by x to get x plus 3. That tends to be a little bit messy. It might be worthwhile to use an algebraic fractions ratio method for this question. Since we know these are similar, it means that the lengths for the base and for the height of the triangle must be in the same ratio. So we can say as follows. We can say this divided by this must be the same as this divided by this. So we say as follows. X plus 3 divided by x must be the same as 4 divided by 3. Okay, just to show you an example where that works, if we had, let's just use some numbers. Let's say this was 2 and this was 4 and this was 3 and this was 6. We can see these are similar because both pairs of lengths double. So we can say, look, 4 divided by 2 is 6 divided by 3. They have the same scale factor. That is the property of similar shapes. Like I said, alternatively, you can work out the length scale factor as 4 divided by 3 and then multiply it by x to give me this. Then you're just going to get horrible fractions. It's doable. You can do it that way. I think this is easy. Now we discussed that if you have two fractions that are equal to each other, we can cross multiply. Multiply the x plus 3 by 3 and multiply the 4 by x. We have to use a little bit of algebra, some brackets. So 4 times x is 4x, 3 times x plus 3, use a bracket. It's not 3x plus 3, it's 3 times the bracket of x plus 3. Keep on going. 4x is 3x plus 9. Subtract the 3x, and if you subtract the 3x, you just get x, which is quite nice. So x is 9. If I were you, I would check that works. I've come up with the answer of 9. Let's see if it works. Let's put x back in. If x is 9, then that allegedly would be 9. And if x is 9, you have to add 3 to it, so it's 12. Okay? So let's see, do we have a common scale factor? Let's see, 4 divided by 3, okay, that's the length scale factor from 3 to 4. Is it the same if I apply it to 9? So let's take 4 over 3, the length factor, which we knew already. If I multiply it by 9, the question is, do I get 12? So let's multiply this by 9. Remember, when you're multiplying by an integer, you just divide by 1. 4 times 9 is 36. Divided by 3 is 12, so it works. Okay, so question 14, we're told the surface area as a ratio, and we're also told the volume of shape B, which is 10 centimeter cubed. We have to get the volume of A. So again, there's two ways we could do this. Okay, if the surface area is 16 to 25, what we can do, like usual, going from surface area scale factor back to length scale factor, square root. Now the factor to ratio, we've seen before that it doesn't actually matter. So if the surface area as a ratio is 16 to 25, then the lengths as a ratio would just be, see, is the square root. Notice they've given you numbers that are square numbers. That's not a coincidence. Let's square root that. We get 4 and 5, except it wants us, it's asking about volume. So I don't want the length ratio, but we need to go back to the length ratio to go forwards to the volumes ratio. To go from length to volume, u cubed. So 4 cubed is 64. 5 cubed is 125. Now, this is A, this is B. So we're going from, as a ratio, from 64 to 125. Now you can convert that to a volume scale factor, which is 125 over 64. If the volume scale factor is 125 over 64, but you're given the higher volume, right, you just take the higher volume and you divide by that scale factor. So now I'll do 10 divided by 125 over 64, which is 128 over 25, or 5.12. I did say there was a second way to do it, and that is dismantling the ratio straight away. So if you're given a ratio, in this case of surface areas, you can go straight to the area scale factor. Okay, the ratio from A to B is 16 to 25, so in other words, the area scale factor would be 25 divided by 16. Okay, so if it was, the ratio is 1 to 3, you would say the area scale factor is 3. Okay, B is 3 times as B, 3 divided by 1. So if you want to turn a ratio and represent it in a fractional format, you just do 25, in this case the right divided by the left, going from the smaller to the bigger, which is usually the way we do things. So the area scale factor is 25 over 16, and now you just do it completely like normal. Again, we're looking for the volume of A, so you have to go backwards in order to go forward. So the area scale factor going back to the length scale factor is square rooting. And when you square root a fraction, you can square root the top and the bottom. Okay, I wouldn't just type that into a calculator. It's actually more efficient to not use a calculator. The square root of 25 is 5. The square root of 16 is 4. That's the length scale factor, 5 over 4. Keep it as a fraction. The length scale factor is again not what we want because we're talking about volumes in this question. So the volume scale factor would be the cube of 5 over 4. Once again, when you're applying a power to a fraction, you could do the top and the bottom. Separately, 5 cubed is 125. 4 cubed is 64. So like before, our volume scale factor is 125 over 64, going from the smaller to the bigger, but we're actually doing the reverse in terms of what the question asks us. It wants the volume of shape A. They give us the volume of shape B, which is clearly the bigger one. And you can see that from the ratio, any ratio, okay, that they would have given us. Okay, since the bigger number is on the right, that corresponds to B. So in other words, you do 10 divided by 125 over 64. And once again, you get 5.12 centimetres cubed. In 15, we are given the volume of both shapes. So it makes sense to work out the volume scale factor first, since the volume is what we have in both shapes. We don't have any other information. So that's the only scale factor we can work out. So let's do 960 divided by 120, which is exactly 8. So that's the volume scale factor. Now, it asks us to work out the surface area as a ratio. Now, we've seen already that the ratio of areas is connected to the actual scale factor itself. It's asking about the ratio of surface areas. So let's work out the area scale factor. Remember, surface area and area makes no difference in terms of similar shapes, the topic, similar shapes. So the area scale factor, I need to go from the volume to the area. Remember, you can't do that directly. You have to go back to the length scale factor. So from the volume back to the length scale factor, let's write it down here, you have to cube root. So I will cube root 8, which is 2. And then I'll square that back up to 4. So cube root to get to the length scale factor and square it to 4. So the area scale factor, or in this case the surface area scale factor, is 4. Now it asks us to write the surface area ratio between the small cone to the big cone. Now if the area scale factor is 4, that tells me that the area of the bigger cone is 4 times as big. Which means, as a ratio, we can write that as 1 to 4. 1 to 4 means cone A and cone B are in the ratio 1 to 4 means the cone B is 4 times as big, which is what area scale factor means.